Hello everyone and welcome to lesson 4 on this energy series. Today we're going to be looking at Hooke's law or spring force law. Basically springs. Anything that's springy or elasticy has this sort of property to it. And here's one way to think about it. Here's 3 different scenarios. Imagine these are all the same spring. If we just left the spring to rest, and also this could equally be, well, no, it could be an elastic band, but elastic bands are a bit weirder because they don't compress in the same way. So just imagine a spring that's resting, it's laying there on the desk, and it has a particular length. And of course you can compress the spring, in other words you can push it together, or you can stretch the spring. Okay, now that would be you applying a force, but as we know from Newton's third laws, whenever there's a force applied, there will be a reaction force. In this case, the reaction force is coming from the properties of the material, in this case the properties of the spring. It's kind of like the ability of this spring to restore itself back to its original position. So if you start from here, this equilibrium point, if you compress it, this distance x, then the spring is going to exert a force on you wanting to come back to this equilibrium position. It's the restoring force. The force of the spring is going to want to go back to its equilibrium. Equally, if you take it from its equilibrium position and you stretch the spring, this distance x, the spring is going to want to pull back towards the equilibrium with this force restoring, or this spring force coming back. Now, that means that there is a displacement factor, there's a force going on, and then we also come across this new term K. K is just a spring constant. It's a number that is associated with that particular spring, and it tells us essentially how stiff the spring is. A large K constant means it requires a large force to move or stretch the spring, and they're all proportional. So again, these are ideal springs. In a real world, of course, the more you stretch, the more you press a spring, eventually you can break the spring. But in this case, we're going to assume it's an ideal spring. The more you stretch it, the more force there is restoring. And it's a linear relationship, it's proportional. So there's the displacement x. The greater that x, in other words, the greater the stretch, if this goes up, then the restoring force goes up equally. In other words, the restoring force of the spring is proportional to how much you stretch it. The spring force is also proportional to K, the spring constant. Now, because these two go in opposite directions, the force of the spring and the displacement moved, because they go in opposite directions, notice that we have this little negative factor in here. So just pay attention to that as we go through. That will become a little bit of a thing. Okay, so we've been introduced to Hooke's law. Now, it turns out that when you use Hooke's law and there's various ways to do it. You can combine some physics principles together to get an equation for elastic energy. And just really briefly giving you a bit of a background on this, you'll recall that when you're looking at a graph, let's imagine we have a graph that is the restoring force of a spring versus the distance. And let's imagine you're applying a force continue. You're going to increase that force over a distance. That's a nice straight line, and you'll recall that it's possible to do one of two things. You can either look at the slope or the area. Now, if we look at the area would be underneath the graph here. Let's go ahead and just color that in. So it'd be this area here, for example, and then the area of that triangle would be the force multiplied by the distance. And you'll all remember that force times distance, well, that is work, which is a type of energy. Okay, now in springs, we just determined that the Hooke's law is kx. So have a little look. If you work out the area of this triangle, it is going to give you the energy of the spring, and that, so let's write this out again, the spring energy is going to be force, the restoring force of the spring, which in this case is kx, and then that's multiplied by the displacement. Well, the displacement is x, so that's kx squared. Oh, and look, it's a triangle, so that would be half kx squared. Amazing. Okay, so let's talk about more about the actual equation and how it can be used. Here we have a 500 gram mass sitting there, suspended, so it's not moving. That means the velocity is going to be 0. So if the velocity is 0, then we're in uniform motion, and that means that my F net is going to be 0. And the forces, well, the forces, there is going to be an Fg pulling this down from the mass, but since the F net has to be 0, there will be a force coming back up, and that's the restoring force of the spring, the spring force. So we have a little physics principle going on here with an F net. We're going to say the F net is the sum of all the forces, and that's going to be 0. And the forces are going to be the spring force coming up and the Fg going down. They are indeed going to be the same. So Fg equals Fs, and the Fg is mass times gravity, and the spring force is Kx. Now, the amount of energy this system will have is going to depend on the displacement and, of course, the spring constant. So let's just make it a little, we'll restate the equation for the energy. It's going to be 1/2 k, the spring constant, times x squared. Now, if we knew this value, which I'm going to give you in just a second, then we can go ahead and solve this equation for the spring constant and then insert it in. So let's just go ahead and do that. Let's just finish this off here. We're going to say the spring constant is going to be equal to mg over x. This can now be inserted into this equation. So we can rewrite that as spring energy is 1/2 mg over x squared. Well, this x cancels with this, so we're left with, let's just write it out nice and simple. The spring energy is going to be 1/2 mgx. And so if this spring stretches, let's just say it stretches 10 centimeters as a result of this mass, that means the spring energy in this system is going to be, well, we've got the 0.5, so 0.5 times the mass, which is 0.5 kilograms, times gravity, 9.81 meters per second squared, times the distance, 10 centimeters, which is 0.1 meters, and that gives us a value of 0.49, and that's to 2 significant digits, but we need 3, so 2491, and that's going to be joules. Let's just check our units. We've got kilograms, so let's just check that we've got the right units. Kilograms, and then meters over seconds squared, and then squared. That's kilogram meters squared second squared. That is indeed a joule. I'm pretty happy. There it is. Okay, so last example question of lesson 4. Bit of a prelude really to lesson 5, where we get into energy conversions more proper. But for now, let's just think about the way energy can, sometimes we call it flow, sometimes we call it transfer, sometimes we call it a transformation. Remember, we don't really know what energy is. It's a weird thing. It's not actually a thing. It's a weird concept. It's very abstract. It's not a fluid. It's not an object. It's a number. It's an abstract accounting mechanism. And so when we do accounting, just like when you're keeping track of money, you want to keep track of the money coming in and the money going out. And in some cases, that money is used to buy other things. For example, you might buy some foreign currency. You might use Canadian dollars to buy American dollars, and there would be some conversion going on. That's kind of analogous to what's happening here. So we've got two ways we want to think about this energy transformation or transfer. One of them is we're going to call a transformation. That is when energy literally changes from one form of energy to another. So for example, gravitational potential energy can turn into kinetic energy. For example, if you were to take a ball, hold it up at a certain height, let's say 2 meters above the ground, and at that point it would, by your definition, have gravitational potential energy, but since you are also defining it as being stationary, it would have no kinetic energy. And then if you released it and dropped the ball that full 2 meters, we would describe the energy being transformed from gravitational potential to kinetic. Of course, we can also do work on an object, and when we do work on an object, we normally talk about forces. And so when two objects interact and their forces are interchanged, or there's a force of one object onto another, then we can also talk about this energy going from one object to another. And here we've got an example of a bat and a baseball. So let's look at a few examples, and hopefully it becomes a little bit more clear. And then in lesson number 5, we're going to do more specific calculations and work on this type of thing. All right, so we've got this object, and it's going to be compressed down into the loaded spring position and then released. So we need to think about the energy conversions of all these different phases. First of all, we're going to think about the release of the spring. So the moment that spring is released and it fires this object up the ramp, then we're going to consider the as the object is moving up to its maximum height in the air, so at this pinnacle of its projectile motion. And then we're going to think about the object as it moves down to the water, and then finally as it hits the ground. So as the spring is sort of loaded down there, we're going to have to push the spring this way, which means the spring is going to be pushing back on us with this spring force. So it's in its loaded position, it's going to have some energy. So hopefully you can see that in its locked and loaded position, we have entirely spring energy. That is going to be converted, well, immediately to move this object at all. Of course, it has to literally move. So that's going to be some kinetic energy. And then as the spring keeps pushing, it's going to gain some height. So if we take this to be our 0 height, as it is moving up the ramp, it's also gaining some gravitational potential. So we have all of the spring energy being converted into a combination of kinetic energy because it has to move, but it's also gaining some height relative to my 0 height. So it's going to also be gaining some gravitational potential energy. Then we need to consider it as it's moving up to its maximum height. So this would be as it's moving. So there's no more spring involved here. This is an object that is in motion. It has kinetic energy, and that is going to be converted into gravitational potential energy. Now, as it's at its maximum height, we also need to consider that it would have still a velocity in the horizontal. So I'm going to just add on here that the kinetic energy doesn't entirely disappear. This projectile motion would be in motion for the whole time, albeit at the maximum height it would have 0 y velocity or 0 vertical velocity. Okay, then it's heading back down into the water. Well, as I said, it has some kinetic energy at the top of its motion, but it also has its maximum gravitational potential energy. So I'm going to add those together, and this will then be converted entirely. So as it's coming down to the water, so it's doing this little bit of its motion, the gravitational potential energy is going to disappear entirely, and we are left entirely with that kinetic energy of the object. As it hits the water, well, we are left with the entire kinetic energy of the object. Let's write that in. And that kinetic energy of the object is going to be converted into, well, it's hitting the water, and there's lots of water molecules, and they're going to be hit by the object. So each of these water molecules is going to experience a force which is going to do work on those water molecules, effectively pushing them and giving them some kinetic energy as well. So there is a kinetic energy conversion from the object to the water. And if you're interested, you can check this out, because it turns out that kinetic energy is also heat. So this could be described as, I guess, heat dissipation. So just keep that in the back of your mind as well.